All right, I'll try to, in the coming minutes, I will describe your story. And please do not call me professor, just call me Yiannis. I will feel much better and more close to you. I feel awkward with the term professor. We do different things in the group, but I think I try to put pieces together so you can take something home. But we've been exploring also other avenues. So if you find something, maybe from the papers that you would like to discuss, of course, we can discuss it afterwards in the Q&A session. So it doesn't have to be in the slides. I'm open to any discussion you feel like having. Yes, a very big thank you to Professor Jong-Hoo Lee for making this possible. In the slides, you will see, again, a compromise of what we want to share. I wish I could speak for hours. What we can share, and eventually what we have time to do. And if there are errors possible, please let me know. I'll be happy to change them. Of course, embarrassed, but still good to know. All right. Now, the presentation has, in fact, 3 pillars. One is about hot stage engineering. The second thing is about processing. And then hopefully we come to something being end products, more downstream. Why do I start from hot stage engineering? It has to do probably with historical reasons. So the group here initially, when I was with Bart Blampin, was on the metallurgy side more than building materials. So that was a starting point, but hot stage processing or high temperature processing is still part of the agenda for obvious reasons you will see. By processing, imagine everything that comes after the slag has been produced or the glass. So anything from milling, this photograph is from flotation, but keep it wide. And end products, again, can be a variety of different things from fibers. You see here in the photo, mineral wool or glass wool, all the way to bricks and tiles and panels. Now, I wouldn't like to keep it too academically in the sense that when we work with slags and industries, ideally you try to offer a solution. So for me, that translates into 2 things. One, it should be environmentally correct and ideally financially sustainable, so your solution can actually be implemented. And if it doesn't happen this now, at least in the foreseeable future. And when we speak about the process, it should be, of course, feasible, robust, safe, and by design upscalable. So you will see that part of the selection, part of the things we do aims in this direction, aims to something that it is realistic, not too much high-level dreaming. Now, why and what's the motivation? I tend to ask these questions. I tend to ask the why, the how, and the what quite often. I'm being accused for a Greek and a philosopher, but I think we should be asking the why. I think in most of the cases, the drive is environmental. We care for the environment and we want to create something better, meaning of lower environmental impact. And that implies we need to change the process. But I find it difficult to decide what you want to do because everything happens fast and concurrently, which means there are many different options and the whole political also landscape is changing at the same time. So not only you need to see the technical availability or the technical upscalability of what you choose, but you should also somehow estimate what it's going to be like. And if you have access to green energy, hydro, for instance, or hydrogen or electricity, cheap electricity. And that creates a whole different exercise. At the same time, industries and businesses want to keep on being profitable, otherwise they are not anymore a business, a viable business. So you need to somehow balance these 2 trends and come to hopefully some peace. Here is an example of what happens in the States. I guess you understand from the source who the author is, Chris Pistorius. And United States is quite clear in going steadily, at least some years ago, I don't know what's going to be now, the style with the current administration, towards electric arc furnaces. That is again interesting because it implies that there is a supply of energy. So 1, you need the energy. 2, that energy should be green by design. Otherwise, the whole intention of reducing your environmental impact, I think it's in vain. Different technologies also come with a different CO2. impact. You see it on the right side. So again, it's a discussion, what is the most appropriate technology to adapt. I find this table maybe a bit nicer for my taste, at least, because it's not only speaking for the CO2 per ton of steel and what is the potential, but it also makes this projection in the future. And of course, yeah, a projection is by design has a high risk, but it gives you the current TRL, which stands for technology readiness level, and the expected market entry, which can be anywhere from 2030 to 2040, or maybe even later. So some technologies can really be very, very impactful. But of course, there are some technical challenges before there is a TRL9. And you will see in the coming slides that sometimes reaching TRL9 is not good enough. Now, interesting, the question is also to what extent we care for the environment or for the CO2. And CO2 is part of the whole agenda and the environmental impact, but it's not only the CO2. So here's an example about price of CO2. Interestingly, also South Korea is mentioned. So the current price in the European Union is about 69 euro per ton. In South Korea is about 6 euro per ton, according to this table. So you can ask yourself, does that mean there's a different motivation in getting things done? And is the 69 euro per ton actually stable? So can you really plan your business and your activities taking that into account? And that's important because most of the solutions we try to develop come from a request from the industry. We want to reduce our environmental impact. But if that is not associated also with a monetary impact, then I think the solution will only be a technical solution, but will not actually be implemented. And that will be a pity, because eventually then you don't actually change anything, but you create a solution only for the future. But I wouldn't mind seeing things happening fast. Here you see prices about CO2 in Europe, and you can see that, but anyway, the value of CO2 is changing. Interestingly, now this has created a whole market around carbon. So there are also side effects of the policy. There are also nice websites, Carbon Market Watch, an example, that you can see and get informed of what's happening. And for the past at least 4 years, there is a steep increase, now kind of steady for the past at least 2 years on the 80 or 60 euro per ton, between 60 and 80 euro per ton, the value of CO2. Future scenarios, depending on what it's going to be like. And again, these are policy related. So this is the forecast. Here's the high quality. Here's the voluntary market scenario. Here's the removal scenario. Prices vary vastly, anything from 13 or 14 up to 238 euro per ton. And that creates, I think, some uncertainty if you really want to plan your business. But interestingly, if you go deeper into why is the price now at 69 euro per ton in Europe, there's a whole background of and factors that influence that. And I was trying to understand better, what do we actually mean by that? And is it the market, in fact, dictating the price, or it's something beyond the market? And I think this is beautiful. This is from a paper of 2022 in Nature, where we speak about societal cost, or the social cost of carbon dioxide. And you can see in the first paragraph is the monetized value of the damages to society caused by an incremental metric ton of CO2 emissions, and it's a key metric informing climate policy. Now, you can do that for climate policy, but you can also take that into account when you design your business. And for me, that has an impact when I'm designing also my research, because I want to do something with the CO2 and hopefully also beyond the CO2. The value now in United States back then was calculated at $185 per ton of CO2, which was higher than the value then, which was 51, which is very, very higher than the value now. So again, you see that there's a whole discussion about that, but the societal cost, I believe in it as a concept, and I think we should also consider that. Here is a recent example. It was initially from Bloomberg, but it goes back into University of Chicago professors, which is again an irony, you will see why. And they try to estimate the cost of climate change. And what does that mean? And if you think of it, you can actually make the estimation in maybe at least 2 different ways. One is you can find the damages that have been produced or have been occurring due to the CO2. And here you see the case in the US. So they had all of these weather and climate disasters, and they put a value on that, and then they say, okay, so that means the impact of the CO2 emissions has this financial impact, thus the value of CO2 is this. Now, the title is big and of course a bit catchy. The price of corporate America's carbon emissions, 87 trillion. And it's interesting because it means that actually in simple terms that the industries do not create enough value. They create more emissions or impactful emissions. So the liability is higher than the market value. So more misery than beauty created. But again, you can also go back and ask yourself to what extent these are America's carbon emissions creating that, because it's a global thing, and to what extent also humans have induced that disaster to themselves by, for example, building houses in a forest without taking any precautions on adapting the landscape so they live more safely, or perhaps being less greedy and not building a house in the forest. Okay, I'm referring now to the Los Angeles fires that I think is part of the calculation here. Of course, you cannot prevent hurricanes. You cannot prevent also, rains and storms, but it's interesting. The background of that discussion, and I put it here from the paper that is feeding the study, and there were two major papers on that, besides the Nature paper, is from the famous doctrine of Friedman. So economics professor at University of Chicago, and the irony is that this is coming from University of Chicago, and it has to do with externalities. So for Friedman, companies should essentially just maximize the market value and to some extent ignore externalities, but that is now in conflict with the welfare of the shareholders, who also have, I'm saying here, they say here, social and ethical concerns. And this conflict is particularly strong with externalities. Social cost or benefits are large relative to a firm's market value. So I find it very philosophically intriguing. Eventually, what do we want to have? Do we care for the side effects of our businesses and of our activity as humans, or we just try blindly to maximize the profits without caring much? That discussion is only for CO2, and of course, you know that there's much more than CO2. Climate change is the CO2, let's say, mostly the CO2 domain, but there is eutrophication, land use resource depletion, all of these different categories that you can find if you want to do a life cycle assessment. And interestingly for me also, what's the price of any of the above? So I'm thinking, what happens, or how can you put a price tag if my kids do not have this variety in options or variety in beauty? If they see one treat, if there is only one fish, one type of fish, and so on. Discussing that with a colleague, she informed that, Yanni, there is a price for everything. These are typically insurance companies. You have a price also. There's a price tag also for your own life. And again, it goes into this semi-metaphysical or semi-meta-philosophical discussion. What is the price and how objective that is? But okay, this is maybe for the discussion later on. So interestingly also, even if we take into consideration the whole package, I think to some extent we think in silos. And what do I mean in silos? The industry, and every industry, and for God's sake, this is not to blame anybody, but maybe an inspiration for a change. They think of how to basically keep the shareholders happy, how to have a sustainable production, but quite often they ignore the side effects. And I'll give you an example. We want to make now new processes, we want to change metallurgy, but what if the new slag to metal ratio is higher, which means we produce more slag than metal? Or what if this new slag is not performing like the blast furnace slag of today, which means we cannot then use the slag to make blended cements? And that's interesting because then in your quest for beauty, you end up again having the side effects that ultimately might create problems, and problems collectively, not only for your business, but also for society. And ultimately for me, the sustainability it's something that should be addressed in a wider spectrum, not just for the metallurgical process or for the building material process. And you should assess the interaction with the nearby industries and eventually the society. And I've described that by the word, total net positive, not just positive per industrial sector. So my wish would be that we think wider in a symbiotic manner. And for the particular, I think, context here, I see that energy, metallurgy, and building materials are interlinked, and they all contribute to CO2 emissions. So I would be happily advocating of creating slags that work beyond metallurgy so that we deliver interesting slags also for other sectors. Of course, yes, I understand we need to respect the metallurgical boundaries and the process. Now, guiding you now more into how we can do that, because I think the first part was more about the why. One of the options is that we transform the slags into supplementary cementitious materials. And by that, a bit of a background, what is a supplementary cementitious material, or SCM? Think it kind of, lightly. You have the cement, you add something that can be TBFS, can be fly ash, can be calcined clay, or a combination of the above. You bring them together, and then you have a new cement. Typically, the term will be then blended cement. And that cement is not simply diluting the Portland cement, but actually it's also behaving better, at least in some circumstance or in some properties. So it's not dilution of cement and performance. In most of the cases, the performance is enhanced for a particular application that this blended cement is directed. These blended cements then have the SCMs, two major families. You can have them as hydraulic or latent hydraulic and pozzolanic, but that again can be for the future discussion in the break. What we want to do, and here you see a snapshot of the European standards. Careful, European standards are not the same with American standards. I'm not familiar with the Korean standards, but long story short, it means that you take in the first column, you take here something, in this case is the clinker, and you have all of the additives. And ultimately, besides the first line, which is the only, let's say, pure cement, Portland cement, all the other things here and more things not in this table that are now into our life, these are the blended cements. And in the US, they also have blended cement standards. What we want to do now, we want to bring this iron-rich glass there. So we want to make more blended cements. And the question is, what should this iron-rich glass be? Why should it be an iron-rich glass in the first place? Who is this idea serving? Is it serving also the performance of the cement or some vested interest? And how do we make that actually contributing to the whole net positive I was describing before? That's what I will try to guide you in the next slides. If we do that, then it can also be an opportunity for reducing the cement clinker in the first column and introducing a new column to the right, where we actually now have this iron-rich glass. And we can discuss on the term. It should be iron-rich glass, iron-rich slag. It should be called iron-rich pozzolana. For me, this is not so important. It should be something that most people at least should feel comfortable, and it should be, of course, precise and scientifically correct. Now, if we start doing that, and this is, again, in a parenthesis, in an ideal world, you can also think, shouldn't we change the whole standard actually? Now, we should change that in two ways. One, cement standards are prescriptive. What does that mean? They describe a material, and in this column, you see blast furnace slag, here you see silica fume, here you see pozzolana, here you see fly ash. They are not performance-based. What does that mean? It means if I make something that actually has performance equivalent or superior to a cement today, including durability aspects, I cannot call that cement. And that is a bit shocking if you come from a metallurgical background where you can have all of these alloys and nobody's asking you on the prescriptive. They describe or they ask you for the performance, prescriptive side. So this is the reality now in the cement world. This is not necessarily the reality in the US. You have also performance-based standards. Australia is probably, forgive me Australians for saying that, but the standards are even much more narrow than the rest of the world. So that was the first thing. The second thing is that when you say blast furnace slag, that implies blast furnace slag from iron production. And the question is, why don't you say instead the chemistry and the mineralogy of that thing? Because one day, same thing for fly ash, we might not have the blast furnace slag that you have today. So why don't we change the name to describe the material instead of the process that creates that material? And I think that's also very interesting. And I think we should be doing that because many of these processes are becoming obsolete, at least in some parts of the world. And at the end of the day, for cement's sake and performance sake and societal sake, we care for the material, and the material is agnostic if it came from a blast furnace or if it came from my garage. If it has the right chemistry, mineralogy, it should perform in the same way. So, okay, I call that in an ideal world, maybe for the future. Let me give you now two examples. You see here one of my favorite examples because I've done my PhD on red mud, which we now call bauxite residue. This is a site where we humans dispose bauxite residue. That means every time you use aluminum, you should think you go back. Aluminum most likely has come from alumina. What else? And alumina most likely has come from bauxite. Okay, this is a most likely indeed. There are also other processes to develop alumina. And that implies bigger process. That implies lots of waste. So we have reserves more than 4 gigaton and annual production globally about 150 million tons. And you see here somewhere up that this is the size of the car. What do we want to do? We want to make something out of that. In this case, you take, let's say, anything from 75 to 90% bauxite residue. You add easy things, silica and calcium. So I'm not talking about fancy fluxes, maybe some carbon. You will need some carbon, depending on how you do the process, because you want to convert that into a non-ferrous metallurgy slag. You want to go to the phyalitic region that is melting around 1200 degrees. Depending on the exact chemistry, and use that as an SEM. So you pelletize, you vitrify, then you quench, and then you do the milling, and then you have a fine black powder. Now you can do different things with the powder. You can make inorganic polymers. I will explain that. Hybrid cements, blended cements with Portland or with calcium aluminate cement. During the vitrification, you see here what's going to be happening. You also make spinels. Love the spinels, please, because they take some of the nasty elements. Also chromium will go there and it will not leach afterwards. Or you can also have iron. Of course, you can do smelting. You can reduce all the way down to iron. Then you have a glass that is now depleted in the iron, of course, and it has more calcium, silica, and sodium. This glass is more reactive than this glass, but of course that implies higher temperatures and of course more reductants to get it done. Here is an example of European BRs. So you could be adding either calcium or silica or calcium and silica that you see also in the Sankey diagram here. Here is your love. That's where you want to end up. And this is your region. Here you find the different percent of melt. And here you see, okay, in this case was 78 weight percent BR, a bit of silica, a bit of calcium, a bit of coke. And eventually you have something amorphous because we do also fast cooling, spinel, wustite, and the likes. And that material is actually very, very good in terms of performance as an SEM. Now, stepping back, what we want to do, we want to go beyond the BR. We want to bring together all the non-ferrous metallurgical sector. And by non-ferrous metallurgical sector, I speak for copper industry, lead industry, alumina industry, and make them all converge and agree on a star. And we call this the North Star, like heading in a certain direction, where you actually convert either from the high temperature or from the low temperature towards this goal. And this is the final chemistry. So we're saying if you actually make it to that final chemistry, and we have papers supporting that, and Holcim has checked that, Heidelberg has checked that, Sika has checked that, the performance is good. Occasionally better than the blast furnace slag of today, but this is again for later to discuss. If we do that, then collectively, I think we create this new commodity that is now high in volume. And I also believe then the legislation will follow, because then you bring together so much more material that can actually be valorized in a high-end application, being blended cements. Again, conceptually in the lab, and then you will see also in a bigger scale, we have the mixing stage. This is, yeah, a drum with a mixer up, and here's a filter press that you see now from the other side here. You create, we call it our sausage, and your sausage is in fact your pellets that you can then melt or use a rotary kiln or an EAF, we can discuss that, and eventually create the granules. What do you do afterwards? Here are again the different terms, but now you see the additions. In the first case, you add a sodium silicate solution or potassium silicate, doesn't matter. Sodium and potassium is also possible. In the second case, you have a very low amount of alkalis. Also, interestingly, these are solids, sodium carbonate, and you just add water. Careful in this case, this is usually in a solution. In this case, it's just solids and addition of water. So this is like business as usual from a processing side. And in the third case, you don't have any more alkalis, and the VBR here is less, and that's the blended cement. This is totally business as usual today. Performance is changing, varies depending on the mix design. Here you have very, very high performance, also on early day strength. You can exceed easily the 100 megapascal. Here you have good performance, but it's a compromise between performance and environmental impact. This particular family has the lowest environmental impact, and this is very good also performance. So it is meeting the standards for, in this case, the high-end cement. And we think it's probably the easiest way forward. I would assume, and I put also 2 more slides here, that some of you have an interest for BOF slags, because ultimately the idea is not that different, and we think of that as a triangle. BOF slags, also being iron rich, can also be reprocessed at high temperature in a similar way. And these are from examples we've done in Sweden, where we modify the slags. Here you see the performance for alkyl activated materials. So anything from in 30 days from 60 to, can't see that one, again, close to 60 or 55 megapascal. And the performance is lower if you do blended cements. So no alkalis here, but you can still reach 20 plus megapascal in 28 days. So this is still decent for many, many applications. Again, these are the extra slides I added today. If you want to visualize the process, think that you have a molten slag. The question is, what do I add in order to hopefully reduce the liquid use so that you add something at room temperature? You don't need to add extra heat. That's important. And you want to end up in a final composition after cooling that will be reactive. So you need to think, okay, what if I also do cooling fast, typically quenching? Do I have a glass forming? Yeah, high glass forming ability in my melt or not? In this case, we added alumina and silica. And these were the 2 end chemistries. And if you want again to visualize in a Sankey diagram, 85% was the master slag, addition of alumina 11 and silica 5, and you have now this final chemistry. Interestingly, because you have higher calcia here compared to the blast furnace, here you have also the calcium silicate, which is a classical phase in cement, and high amorphous content. And this is behaving quite nicely. You've seen before, both from an alkyl activation perspective and a blended cement perspective. So conceptually, now stepping back, nobody wants to mess up with this step. This is the money-making element, the metal. So you separate the metal, but you still have a molten slag. Then you think of your additives, calcium, alumina, silica, or anything that makes sense for your process. Ideally, a commodity. So you make a process that is easy for the whole world. You can start from the molten, or you can start from low temperatures and heat it up. Then you granulate. You can do that wet granulation. You can do also dry granulation. Your new slag is here, and then you have these final products with fibers, with porosity, or with, in this case, zeolites. Depending on the cooling rate and how you do the granulation, you can have, again, from the same glass, from the same molten phase, from the same slag. That's what I want to say. You can have an amorphous or almost fully amorphous material, or a material almost fully crystalline. And this is for a copper slag we've done, modified copper slags, not the typical composition, different cooling rates, and you find, of course, different crystal morphology. Why would you do that? In some cases, you want to have aggregates, and I think this is making more sense if you want to have aggregates than that. But if you want to have a binder, quite often this is preferable. It's not necessarily you need 100% amorphous. And again, conceptually, you go from this black to this black to this black, powder, slurry, and eventually product. And we can also discuss, atomic arrangement and how you end up from a first material being molten. How do you make this depolymerized, eventually glass that you can actually easily dissolve with the alkalis to recreate an arrangement of atoms that actually gives performance and durability in the long run. Now, let's go downstream. Imagine you have the slag. What do you do afterwards? I think 3 are the challenges. If you have the slag, fine, you can modify it. If you don't have the slag, like in the case of bauxite residue, you have to think, okay, how am I doing the process, the high temperature process? So I'll give you some examples. Once I have the slag, how do I choose the proper milling? And the third thing, once you've done the milling, what do you make out of that? Okay. So I think if you can answer that, if I can answer that, anybody, we might have a whole making sense story. Here's what we've done for the bauxite residue. The idea was bauxite residue contains iron. Let's use of the iron. So instead of trying to, let's exploit that opportunity. And iron, depending on the oxidation state, depending on the phase, for example, magnetite is preferable. We will couple with microwaves. So we've done microwaves and it works fine, very high heating rates. We've done induction heating. You will see also a video. We've done concentrated solar power. So imagine, you have these mirrors, eventually have the solar light concentrate on a very, very thin beam that is having very high temperature, and you have a conveyor belt with your material passing and you melt it in real time. We've done EAF, and submerged arc furnace is an option we haven't done. Plasma, we're now thinking of going into that, but we've done in Sweden was a plasma reactor, and resistance heating, that's how things get started. And of course, you can also do resistance heating in a big scale. You can see foundries, and that's what they often use. We've also done top-blown rotary converter, TBRC, and we also done rotary kiln that you will see a slide. This is probably the latest thing. But the last 2 are not electrically powered. So you have, you still use natural gas. So they're bad. Now, how do you electrify the melting? What's the best technology? I don't know yet. I wish I could tell you. My feeling is that eventually will be a best technology per geographical region. If you have access to hydro, access to hydrogen, that can also help maybe. What's the electricity price is a very, very strong factor in making you choose this or that. I can tell you what we want to do. We want to go more into flash melting. So this is the future. If anybody's interested, please let's join forces. If I can do flash melting, then the whole discussion about kilowatt hour per ton will be probably winning, because I can do that instantly. So maybe energy consumption will be suppressed. Second thing was the milling. Here was interestingly also from again, semi-philosophical perspective. Most people, when they think milling and building materials, they think dry milling. Why would you do that? Because 1, it's easy. 2, you wouldn't do wet milling for cement, because the whole idea of cement is that it hydrates, so you don't want water. 3, somehow in the labs, you always have dry milling, or most often dry milling. But if you look into iron ore, wet milling is very, very common, or in fact, the standard. So then if you look into the ISA mills, for example, it's about wet milling. So why don't we do wet milling in the slag? Because the slag will not hydrate. And that's what we did. And then we also twisted a bit the process, and we said, okay, let's also add a bit of alkalis, a tiny bit. So not only we have milling, but we also have in the same time activation. So you basically have dissolution while you do the milling. And then this is, you can also access it. It's a database we create. So we also put things up on the web for people to see and duplicate or inform themselves. We said, okay, let's make a slurry in this case. Here is about 39% the slurry. You have then the cement that you add, some gypsum and so on. You see all the components. Coronel is the slag we have here in Belgium, the copper slag, which we add as an aggregate, about 51%. And here's the plasticizer, also 0.2, and limestone powder. So we've done the milling, and then we've done casting, okay? And why do we do that? Because we want to make an easy process. So if you now think of the slag component, it's about 80 weight %, and the cement is about 6%, which I think is quite attractive. Again, how we do it, we did it. This is the classical way, and we also have installed readouts for the energy consumption in our treator. This treator, you will typically do dry milling, then you will put cement and water. Powder 1, powder 2, plus the water. Here's the performance. Not very exciting. What we've done now, we said, okay, let's do it differently. We do the slurry. So you bring the slurry in a liquid with a bit of alkalis. You minimize energy consumption. Then you take the slurry and then you add the cement and the aggregates, and the performance is better. So it means performance better, less energy consumption, 2 thumbs up. Fun enough, we also see that if we keep the slurry for 24 hours, then the performance, once we add the aggregates, is increasing. So it seems that the dissolution is happening. It's an ongoing reaction. So it would make sense if you also delay your production day. And that's interesting, because it means that you can have less energy consumption in the milling step and higher performance. And these are simple things somebody can do to make it happen. So instead of then actually sending the dry powders, you can send the slurry, and you say in that slurry, add your aggregates and 5% cement, cast, because it's still castable, and you have your building materials. And when we speak about environmental performance or low environmental impact and high environmental performance, here is another example. That was totally rethinking the process. So we said again, okay, let's take now the BR. Let's forget the high temperatures, because nobody wants that. Everybody feels, okay, it's a huge investment. Let's do, we call it, solid state dissolution. So you take the BR, you put a bit of activating solution, you press it, and then you put that in an autoclave. Now, why do I put that in an autoclave? That's how you do the Bayer process. It means that you need high temperature and pressure, and then things start to dissolve. And that's how you do also many building materials. You use autoclaves. And we thought this is a low capex process. And in fact, it does create interesting products that, of course, are water insoluble. And that's all it takes. So you make bricks through this autoclaving process, and you make your monoliths. Here you see microstructure. It's quite dense matrix. And I will show you now another slide, what is forming, different things. But first, let's understand what is reacting. So again, inspiration was the Bayer process. In the Bayer process, when you do autoclaves, and they're different because then it's a liquid, you dissolve the alumina phases, gibbsite, boehmite, diaspore. Same thing here. You will dissolve also silica, like quartz, same thing here. And you see with the lines before and after autoclave. And depending on the conditions, you will form different things, sodalites or zeolites, as we have seen also in our process. Now, from an NMR perspective, you also see clearly that alumina is dissolving and new alumina is forming. So you go from octahedral to tetrahedral, and that confirms the dissolution of certain phases and the formation of your concrenite and analcime. And then you start thinking, okay, how can I make this now better? So you start exploring different additives. What can you add? It should be low cost because you want to make a brick. So you can say, okay, what if I put clay, quartz, limestone, brick waste or mortar waste and so on? And you have all kinds of different now combinations of reactions. So depending on what you add, you create, let's say, different reaction patterns for things to grow. And if you know what you want, for instance, if you want more analcime or more catoite or more CSH phases, you can steer the reaction accordingly to this or the other direction. And that's interesting. Because again, we add 80% of BR 20% of wastes or things that not many people want, and we create a product that actually can be finding an application, can find an application in the market. So summing up, compressive strength is increasing, durability, of course, is increasing. Leaching has been checked. You will see a paper soon. And the advantages are, yes, you create in almost 200 degrees or 150, lately we go, room temperature products that can actually be used. We've done the upscaling. Here you see how we do it. So we dry the BR, then we deagglomerate and we do the mixing in a high shear mixer or a plowshare mixer. Here is a press. It's a terrazzo press, we call it. Here we bring the material inside, and this is now turning, and then there's a piston on the right side. Let's see. Oops. Okay. So it's pressing it, and then you put the tray under, and then you will find on your tray a tile. And then you take this tile and you break it in your autoclave. So everything is in containers. If you ever come to Belgium, to Leuven, I'll be very, very happy if we go to our container park and you see the whole process there. All right. Now some other case studies. We've done self-leveling materials. For us, it's called grout. In this case, you have to see about also initial and final setting times and compressive strength, how it develops. So if you want to make tiles, you can even sell them as tiles, but you need to take into account, of course, your cost, your mix design. In this case, we use a hybrid binder, potassium, so it doesn't also have a fluorescence. And again, it was slag for the most part. Here is nice, but I welcome you to go into YouTube and find the video. It was done with the University of Eindhoven. They provide us the printer, but Glenn did the development of the mortar. And we also compared that to a commercial mortar. It's called Weber is the company. So this one has 31 megapascal in 2 days, 52 in 90 days. We lost the battle on the 2 days, but I think we won with a big margin on the 90 days. Shrinkage, quite low. We are fire resistant. I'm not sure that Weber can claim that. And we think cost-wise, although this is an estimation from us because we don't know the details of the formulation, I think we're not doing too bad. And we could also print higher than the Weber formulation could. So this is not, I'm not saying Weber was bad, it's the best in the market, but if you think about it, it's also not too bad that we could use slags, a quite low amount of Portland cement, and deliver something of certain value at least. This is another story here. We bring now porosity, and here is a compromise between introducing porosity in the material, but not losing sight from the mechanical strength. So the compressive strength is about 14 megapascal. You see here thermal conductivity and the density. And again, we start with a slag that has initial density 3.5 to 3.6 grams per cubic centimeter. So it is a difficult slag, quite heavy to have low density. But we have a process where we introduce this porosity. You can do it in different ways, by foaming agents or by surfactants or a combination of the two. And we made a wall. So I think we made more than 200 bricks, and they were big. They were not small bricks, because we also, or the industry, wanted to see eventually the performance in a wall structure. If you have porosity, you can think of thermal insulation, you can think of sound absorption. So it's also a wall that will be probably creating quieter rooms. And depending on, again, on the particle side distribution, sorry, on the pore side distribution, you have a different performance also from the acoustic side, which is, again, interesting. The formulations that do not have this cement hydration products can also be more fire resistant, and that has been a big thing in the group. Where would you use that? Typical application would be in a tunnel. So you try to protect the concrete, so you put a whole layer of these bricks to protect the concrete in the back. But anything that is exposed at high temperatures or a flame can actually be interesting for these bricks. You have then different tests. They go to different temperatures. Here is the ISO test, but you can go up to, I think, 1340. And yeah, you typically have the flame on one side, and then you see the performance on the back. We've made bigger plates. This is 180 by 1 meter. You see here the performance. They were tested in the ISO profile and how you will do that. This happened in Spain. You have the concrete up here. You have here the panel, you put that on top of a furnace. There are different, again, setups, and you monitor the temperature in the back. So it has to be also a barrier, like a heat transfer barrier, but it should maintain its integrity and eventually protect the concrete in the back. And that's another setup here. And we did good in both standards. I think we did not yet reach the most difficult one, the Dutch standard that goes to 1340. And that is something different now. If you don't want to look into high temperature or protecting high temperature structures, you can also think of creating zeolites. Now, why would I do that? You can do it for the sake of having zeolites, which can mean high specific surface. You can mean that you can maybe encapsulate certain metals. But if you go into in the direction of high specific surface, then you can think that this could actually be a substrate for catalysis, which we wanted to do, but yeah, somehow never really went far. But I can really confirm that there is a way to increase the surface. So yeah, maybe it's an invitation for somebody else here in the room to pick it up and try to see if that will fly. Depending again on the initial chemistry and the conditions, which means temperature and pressure, you can have different things forming. This again is with iron-rich materials. In the particular case, we form analcime and iron smectites. Okay. So high specific surface is the final product here. Now, coming maybe to the second part and kind of wrapping up. At the beginning, I started speaking for this iron-rich glass. So I want to take a bit deeper into this story and kind of update you and hopefully find interface with how we can collectively take it to the next step. If you would be designing a cement, let's say cement to save the world, and there are many, many ways of making cement to save the world, and it doesn't mean that this cement will be actually the cement. I think it will be one of the many. But if we start doing that, let's do it nicely. So I think it will be correct if we have local raw materials, abundant, accessible to all. Let's make it democratic. We avoid carbonates, we incorporate residues, we do not have heavy metals coming in the beginning of the process, or at least living. Living means leaching. We do not have fluctuations per stream. We develop and optimize a process per case. Environmental impact is kept low, and we have also some kind of flexibility on the end products. And we care about cost and environment, not only cost. These are going beyond the Friedman. And yes, we also can adjust by creating AI tools or computational tools to help us in the process and the final performance. Here is a snapshot of Europe. You find here active alumina producers. Maybe you can put an X here. Unfortunately, they're not that active anymore. The biggest plant is in Ireland, in Ognish, but you have still other sites, Spain, Greece, and so on. You have the legacy sites, more than what you see actually. And here you see copper producers. So if you remember, I'm trying to bring now the copper producers and the alumina producers and maybe also the BOF slags together and create this commodity. We call this the North Star plan. Here you see like a Sankey diagram. Here's the bauxite residue. Here are your fluxes, and similar case here. Here you would do it at high temperature. Here you will start from room temperature going up. And we want to converge into something that is good for all. So here's the final product. That's the vitrified material. And then you want to blend that with different things and eventually sell it. And if you sell it, you're happy because then you actually valorize the waste. So you do the circular economy in reality, not only on your papers. Again, computational design, yes, you can do fact-size calculation and that will guide you in what you need to add. Here's an example, again, silicon calcia. You can also choose between the two, also taking into account that calcium most likely will come from a calcium carbonate, so you want to keep it low. This is the process, again, in the lab. You know that already, pelletization, vitrification, then milling. That's the final material, about 70% amorphous. It will work, spinels, we like spinels. And here is the R3 test that will actually tell you if you are doing good. If you are on the 400 plus joule per gram, you're probably doing quite okay. Here is the area of GGBFS. Here is the C fly ash and S-type fly ash. And here's the performance of the different materials we're making. The R3 test is also now standardized, so you can trust it. It will be a good first indication. And that's what you do. That's what you add with the VBR in this case. Then we've done upscaling. This happened in Aachen in their TBRC furnace. We made, I think, close to 4 tons, out of which 2 point something eventually came back to Belgium, and we made products out of them. And then we started going a bit deeper in the process, try to analyze how really sustainable is. Here you see things for the clinker production. You find the total energy needed, anything around 3,300 megajoule per ton. And here is our process, 28. So that's nice. First checkpoint that we actually need less energy than needed to produce the clinker today. This is quite close to the energy needed to have calcined clay in a rotary kiln. Also nice, because the calcined clay is now becoming the product for cements. These are the lime calcined clay cements, LC3. So we are on that range. You can improve that. Here we have things that we have not actually been optimizing, but let's keep it now simple. That first thing is that your energy requirement is fine for making this happen. Second thing, interestingly, is that you will not be using ideally carbonates. If you want, let's say calcite, you can take from BOF slag, you can take from other things that are already decarbonized. So you don't need also the energy requirement for the dissociation of the limestone. That's also important. Where would you see that in the whole process? It's mostly here. The other steps are not so energy demanding. And then you check the LCA and you see that, yes, depending on what you add and what's your source of carbon, you can have different environmental impacts. But in all the cases, you're doing better than the clinker today. So you can even go to very, very low amounts of CO2 per ton of VBR. Then what you do, you make the blended cements. You want to provide this whole range of formulations. So you find here 70% of cement, 30% of your additives. Here is limestone and VBR. And then you increase, you see the colors with the dark gray is VBR, with the light gray is limestone. And then you see performance. And it's good. It's good because 70% still VBR, you're on the 52.5 N. You're a bit short on the 2 days, but then you're catching up. And then in the other formulations, you're always on the 42.5 category. And that is very, very exciting because it means you create now this substitute for cement clinker, but actually you're not compromising on performance. And if you see our latest data and our new formulations, they're even better. But okay, I cannot speak much about them. So there is hope that this can actually also decarbonize the cement industry and save some CO2 from being emitted. Here are the people who made this thing happen. I'm the presenter. And here you see our bench that is now in Greece, hopefully still standing, made with this cement. We have one in Leuven and it's still fine. All right. Now, we have now the new glass. We have upscale, continue to high TRL. This is what happened, I think it was this year. So before I saw you a photograph of a TBRC in Aachen, you've seen some induction furnaces in the lab. This is a bigger furnace, that's a rotary kiln. And the idea is here that, fine, the cement industry is having a production based on rotary kilns. Would it be conceivable or even possible to convert an existing furnace from making the cement clinker into making a melt? For me, it was always, yes, of course. It looked like the Wilds process, but yes, I have this, I think, habit of thinking everything is easy. Here you see the reality though, and it did happen. So we did make, with people of Holcim and people of Czech Republic, we did make this glass in a very, very big furnace, and we have received the material, and it's fine. You need to change the refractories, so but more details you can find in the slag valorization symposium was a presentation, and you can see more in the proceedings. So there is also hope for the industrial upscaling. This is what we've done in the lab. I think it's interesting because we converted an induction furnace into a rotary induction furnace. And by creating this rotation, you have better mixing. So it has been a whole journey for us because we did not have money. So we've been combined bits and pieces. We even had to buy our own power generator to make it work. And this is in our, again, container park. But while doing that, I think you also build a character. On this side, you see the thing for the glass, and on this side, you see something else. We have also been doing roasting, and we made a crucible that is actually, I think this is the nice thing on the crucible, that it has this concentric input where we actually bring the hydrogen, and these were the works of Yiannis. And you can have also rotation, and we have inside also baffles, so for better mixing, and you can do roasting, anything from 600 to 900 degrees we've done under hydrogen, again for BR, but here we're more on the metal extraction. Okay, now I saw you before the dream that one day we have also these new columns. In fact, this dream might happen. So there has been a dossier submitted to the CEN. This is the European Standardization Committee. And they are responsible for the standards also for cement. And there is now a new column proposed on modified processed bauxite. Carefully, this does not mean it's only us falling under that column. It's also the calcined BR. So there are different ways of heat treating the BR, different temperatures, different performance also every time. But we feel confident that with these formulations and occasionally limestone, we can have a new type of CEM2. So I think it's big. And even if it won't happen, I don't know the future, but I think also from an emotional perspective, it says something that we try to create with the support of the industry this time, something new, meaningful. All right, something we can do. I think we can change, and also the younger students here, because let's say the professors, who are doomed, will be dying any day soon, but the future is with the young ones. So I think we can change how we see the whole process. So the fate of the residual stream is not addressed, I don't think, often. So we speak about the metal, we design process for the metal, and we forget, yes, there's a slag also. And here's some examples where I think also in Europe that was not really addressed, or was never really the focus. So I'm doing this kind of, I call it the buying exercise. And what I experience often is that somebody comes to sell slag. And I think there is a confusion here because also communication barrier, like from which metal process step. So slag doesn't mean the same thing for different people. I think for civil engineers, there is a slag, but for me, slag is nothing in particular. It means a whole range of chemistries and mineralogies. And so I think we should change the way we communicate. We should be more precise. We talk for this particular slag from the particular process that is produced in this particular plant that has this particular flow diagram. And then you want to replace a certain commodity, but in fact, that commodity, being the cement, is so well defined, and I feel safe as a business because I know it has been working. So why would I now lose my sleep and bring a slag that is not consistent, that is not performing, that will probably also have heavy metals? So I think these are things we need to fix. And your selling proposition, if you try to get away with a slag, is probably the high volumes. But I don't think this is good enough for things to happen. And this is what I also think we should be doing. We should also look and build up this, competence of understanding as understanding humans. And I think in our program as engineers, we basically focus on these things. We focus on the technical and performance related aspects. But quite often we forget about other barriers in this case, or building up awareness. I think it's more generic. It's about creating this understanding. And ultimately, you have these all things that actually have an impact and influence your success in making things happen. So I described this as a mentality shift. You have these barriers. Here is institutional and habitual, economic barriers. Here are knowledge and perception. And I think it's visualized better in this case because that was from a paper that I cite here for the construction sector. We think that our performance is not good, so we boost the performance, we try to fix the process, but it might be that we're missing certain things. For instance, for them, the barrier was mostly lack of technical knowledge, training, perception, concerns about durability. Not that durability was not good, but they were having concerns, lack of standards, low availability, and so on. And yeah, insufficient fit, whatever that means, it means it's about chemistry. Like, yeah, go figure this out. So thinking wider, also demystifying TRL. In Europe has become big, but TRL 9 does not mean a product is ready to enter the market. Famous slide in my presentations now. You have different values of death. If you reach TRL 9, good for you, but you still need a market readiness level. So you need to bring that to the market. And normally you should be doing these things in parallel because you have these three pillars. TRLs, can we build it? Regulatory readiness level, can we accept it? Market readiness level, will they adopt it? So for instance, one of the things we're discussing about our cement is what is the color? Will it be more dark or will it be same gray? And why should it be the same gray anyway? But if that creates a negative perception, then you really need to address it. So you might have the right performance, but if the color is not desirable, you might not be able to sell it. And if you don't sell it, you don't actually make circular economy. All right. Last thing I think I'm changing in our also way of thinking. We've been trying to think of performance, environmental impact, and cost. But then I'm saying, well, performance, if something is high performing, probably it has a higher value in the market. So the 52.5 cement sells more than the 42 and sells more than the 32.5. So in fact, performance means cost, means value. Environmental impact, go back in the first slides. Sadly, it's typically mostly about CO2. Sadly, that comes with a price. So maybe everything again comes down to money. Kind of cynical, but I think we should also think about it. Is that true? And if it is, then should we have this more than generalized cost optimization approach if we want to push things forward with a positive environmental impact and a high performance? So instead of conclusions, probably I'm finishing 10 minutes before, but I guess we can live with that. Quite a few slides. I'm trying to think, what can we do as academia? I think what we do today is beautiful. We talk, but we can also create international working groups where we bring people together from different sectors, different opinions, different backgrounds, and collectively we try to make something nice. For instance, we identify slag chemistries and mineralogies that work for the cement and the concrete industry. We develop new processes. So there is this cross-fertilization. I was talking to Japan for the Kubota process. You know, you can have inspiration from all these directions, where we capture CO2 also, and then we think of the materials also for different applications. Look up, for example, gravity battery. Very interesting. Why would you use slags as a gravity battery? But they're heavy, and these are blocks that you lift up high. So maybe we should think also outside of the box. And these are the different properties that you want to think. And maybe we can also stimulate startups or somebody eventually making it happen, maybe starting from niche markets. And we also saw some understanding that eventually the non-technical barriers are quite substantial and quite important in shaping reality. Yes, how we do that, we can organize visits, discussions like today, have shared projects, PhDs. I think anything can help in building up more understanding as a community. and hopefully creating solutions. So that was the end. Everything you've seen here today, I think the 99% was not made by me. I made the slides, but of course the materials and the process have been developed by my colleagues in the group. Yes, I have been participating, but I want to say a big thank you to all the people. And of course, we needed money, sadly. So many projects from EU and Rio Tinto have been helping us to deliver the presentation today. If you want to know more, we have a website, it's fremat.eu, and we try to put things together and create this one reference site of what we do. That was it. Thank you very much.